Newton's second law tells us that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. So as an equation, we can write that the acceleration A is equal to the sum of the forces divided by the mass. Now in this case we're showing the sum of the forces with the Greek letter capital sigma to stand for sum. So this is a fairly usual notation that you will need to get used to. So if there was three forces acting on an object, say F1, F2 and F3, then the sum of the forces would be sigma F is equal to F1 plus F2 plus F3, where all of these forces are vectors, so they need to be added vectorially, i.e. head to tail, or you can use components if that's easier. Now with Newton's second law, you'll often see it written as the sum of the forces is equal to the mass times the acceleration. And often when we're solving problems, this is the easiest format to use it in. Let's have a look at a bit of a demonstration now that demonstrates Newton's second law. So what I've got here is a trolley. It's actually got a spring underneath. When I release this spring, it's going to send this plunger out here. And as the plunger's up against the wall, it's going to push off from the wall. So this allows me to get the same force on multiple occasions because I actually have the same energy stored in the spring. So what we're going to do is compare how quickly the cart accelerates when it's got no mass on it to when it's got 1 kilogram, 2 kilograms and 3 kilograms added to it. So let's have a go at collecting those measurements now. So here's a replay of that. You can see in this replay that the trolley with the lowest mass had the highest acceleration, and the trolley with the highest mass had the lowest acceleration. So here we've got a graph where we've plotted the acceleration along the y-axis and 1 on the mass on the x-axis. So you can see this has got a fairly nice straight line relationship, which is what we're expecting because when we stated Newton's law the first time, Newton's second law, we said that the acceleration was proportional to 1 over the mass. So we'd expect acceleration versus 1 over mass to be a nice straight line. So in this case, the gradient of the graph is given by the acceleration divided by 1 over the mass. And so the gradient is equal to the acceleration times the mass, which is equal to the force. And since we were applying pretty much the same force in each case, we end up with a nice straight line here. Let's have a look at an example now where we'll use Newton's second law to solve a quantitative problem. Question is, two forces act on a body with a mass of 2.0 kilograms. The forces are given by F1 is equal to 3.0 I newtons, and F2 is equal to minus 2.0 I over the mass. 2.0 so in this case, the sum of the forces is equal to F1 plus F2. And so this is equal to 3.0 minus 2.0 I plus 2.0 J newtons. And so this is equal to 1.0 I plus 2.0 J newtons. So we've now got the sum of the forces. The acceleration is equal to the sum of the forces divided by the mass. So we've now got 1 over 2.0, that's 1 divided by the mass, times 1.0 I plus 2.0 J. And now we're dividing newtons by kilograms, so that'll give us meters per second. So this is equal to 0.50 I plus 1.0 J meters per second. So we've now found the acceleration in unit vector notation, but it's asked us for the magnitude of the acceleration. So now we need to convert this to a magnitude. So to do that, we've got 0.50 in the I direction, and then 1.0 in the J direction,
and the magnitude is up here like this. So we can use Pythagoras' theorem. So the magnitude of the acceleration is equal to the square root of 0.50 squared plus 1.0 squared. Solving this on the calculator, we get 1.118 meters per second. So we should just present it to two significant figures, as everything's given to two significant figures. So the magnitude of the acceleration is 1.1 meters per second.